First of all, dear candidate, dear professors, members of the committee, dear Ms. Filipovska, I would like to tell a big welcome, a great warm welcome to the master defense of the candidate, master thesis defense of the candidate Filemon Jankuloski, title as Minimax algorithm for a king and rook versus king chess and endgame. According to the procedures and the policies of our university, please allow me first to give you some information how will this presentation look like and what are the steps within. So first of all, our dear and lovely Sonia will present a short biography uh, on the candidate's background as well as his work within this thesis. Afterwards, the candidate will have 15 to 20 minutes to present his work. So, Philemon, please be aware for the time limit. When the thesis, when the Philemon's presentation is up to the end, I would like to invite the committee consisted by Professor Bozinovski as a supervisor of this thesis, Professor Ivan Petrov as a committee member, and me, Professor Stemenovska as a chairman of the committee, to post questions, their questions within in the chat box of the WebEx screen. And once the questions are posted and the Philemon finishes his presentation, he can take a short time, 5 to 10 minutes, to think about how to answer the posed questions. Philemon, you can answer them one by one. You can note them all and answer them at once. And I'm convinced that the questions will inspire also a nice discussion about your work, since it's noticeable that you have done a good work here, and it will inspire. It is a very up-to-date theme, and it will inspire really good not just questions, but also like notes for further research and so on. So I would like to invite the committee up to discuss a bit after the answer, Philemon's answers, and to give him some their overview and tips how can he continue his work in the future. All that process should not be longer than 10 minutes, 15 maybe at most. And afterwards, Philemon, you will have to log off, or we can create another group here to confirm and to organize ourselves in order to decide upon the degree of the thesis. Then you will come back and we will go to the, I would say, the best part, which is pronunciation. You as a Master of Pronunciation, your Master of Science degree. So, is it all clear, Philemon, colleagues? Can we start? Do you have any questions, Philemon, or the others before starting the presentation, or we can start?
Everything is clear for me, so.
But
Thank
I
you.
will read short.
Yeah. First, Sonia, the floor is yours, and afterwards, I will give the floor to the candidates. Thank you.
Thank you, Irena. A short bio about the candidate Filemon Jankuloski. Filemon was born in Skopje, 1997. He graduated high school in Crown Point High School in United States. Shortly after graduation, Filemon went to University American College Skopje, it was 2016, to pursue a bachelor degree. Filemon underwent drastic changes because he had left his old life behind and he pursued for a higher education. Despite his struggles, Filemon was an avid learner and aimed to reach the top of his class with his outstanding work ethic. After graduating, after earning bachelor degree with distinction, cum laude, Filemon wanted to pursue an even higher education. He went on to specialize in software engineering as his master's thesis studies. So far, he passed all the curricula from, he passed all the courses from the curricula software engineering with an GPA of 3.81. That means distinction summa cum laude. Filemon is looking forward to working in a team in the future where he'll assist in developing practical application and where he'll take on new challenges.
Thank you, Sonia. So, Filemon, the floor is yours. I wish you a successful presentation.
Thank you. So, hello, my name is Filemon Jankuloski, and I will be presenting the Minimax algorithm for King and Rook versus King chess endgame. So, leading textbooks on AI define it as the study of intelligent agents, which can be represented by any device capable of perceiving its environment and maximizing its chances of achieving its goals. AI can be found being used in many aspects of our daily lives, such as through the use of smartphones, virtual assistants such as Siri, and autonomous driving vehicles such as the Tesla. In the context of this project, the intelligent agent is a chess-playing AI, which employs the Minimax algorithm and controls the moves of both black and white. The goal of the project is to showcase the Minimax algorithm's capabilities by testing to see if increasing the depth of the Minimax tree will improve the AI's level of chess play. I'm going to skip the literature overview in the interest of time. So the position evaluator is actually what assigns values to all the different chess positions. The white rook, white king, and black king all share a single position evaluator. This consists of two criteria, free squares and endgame values. Endgame values are values which are assigned only when certain Boolean variables are true for one of the 5 endgame situations accounted for in this program, namely checkmate, stalemate, 50-move rule draw, rook capture draw, and threefold repetition draw. So when the Boolean variables are true for one of the 4 drawing scenarios, endgame values would be equal to 1000, whereas if the Boolean variables for checkmate is true, then endgame values would be equal to -1000 instead. So free squares refers to the amount of squares that the black king can move to. As you can see, the chessboard is actually divided into 4 separate quadrants, all of which are relative to the position of the white rook on the board. Once we can ascertain which quadrant the black king lies on, it's quite simple to calculate the amount of free squares that it can move to. Since white wants to restrict the black king to progressively smaller amounts of free squares, such as to eventually deliver a checkmate, white's goal is to choose the moves with the lowest possible value for free squares and for endgame conditionals, since it employs the minimax approach. Conversely, black wants to maximize the amount of squares available to it and achieve any of the 4 drawing scenarios, which is why it employs the maximum approach. So this is an example of the tree of Minimax in my program. Let's say that the root node represents the state of the board before white makes a move. Now, following the root node, all the nodes on the first level will consist of legal white moves. And then following those white moves as root nodes, all of the nodes on the second level will consist of legal black moves. These white moves and black moves are stored inside of linked list data structures, and this would include their ID, their enumeration, and their value. Additionally, the linked list for black moves also contains a value known as the origin. And the origin is a value which represents one of the potential moves that can be made as shown on the first level. So one white move followed by one black move comprises one step of the minimax. But the question is, how do we know which node is going to be chosen as the move to be made? Well, first we need to sort out all the values on the bottommost level of the tree of minimax, which in this case would be the second level. So basically what we want to do is pass the maximum value of each subtree to their corresponding root nodes. This would comprise the maximizing step. And then we want to pass the minimal possible value of each subtree to each corresponding root node. And this would comprise the minimizing step. In the end, we'd be left with just a singular node. And this node has an ID of 7, but it has an origin of 3. So the node with an ID of 3 would store the enumeration for the move to be chosen. Now, let's say hypothetically we're in a situation where there's only one subtree left and we're on the minimizing step. And there's multiple nodes which share the same lowest value, which node would be chosen? Well, in such a case, one of the nodes would basically just be chosen at random. The analogous approach is used when it's black's turn to move, except that the root node represents the state of the board after white has made a move. So all the nodes on the first level consist of legal black moves, and all the nodes on the second level consist of legal white moves. One of the key differences is that we would start with the minimizing step, and then we would follow that up with the maximizing step. So the reason why is because since black employs the maximum approach, black wants the greatest minimum value of all the nodes. And conversely, since white employs the minimax approach, it wants the smallest maximum value out of all the nodes. So this is the user interface of the program. I'll explain it in greater detail during the live demo of the program, which will happen soon. One thing I will explain, though, is what happens when we click the tree button. So when we click the tree button, it opens up a new window with a tree diagram where the root node represents the state of the board before the previous move was made. So the depth of the tree of minimax is equal to double the amount of steps plus the level where the root node resides on. So a tree of minimax with 1 step would have a depth of 3, and a tree of minimax with 2 steps would have a depth of 5. As you can see, each node in this tree diagram is represented by a string of characters and numbers, which in their respective order refer to the value of the move, followed by the coordinates of the black king, white rook, and white king. So nodes can also be distinguished based on what color they are. So for example, this blue node is a checkmate, the gray node is a stalemate, the magenta colored node is a threefold repetition draw, the pink node is a rook capture draw, and the orange node is a 50-move rule draw. Black moves are just normal standard nodes, and green nodes will be explained momentarily during the live demo, which should happen now. Let's see. So as you can see, the user interface of the program is much like a normal chessboard. The frame of the window showcases whether it's white's turn to move or black's turn to move, and it also has many different buttons with varying functionalities. So when we click the README button, it gives a detailed description about how to use the interface and all the buttons on the program. When we click the About button, it opens a window that gives a short description about the authors of the program. Now, when we click the New button, normally it would generate a random legal starting position, but in the interest of time, I've decided to make it so that when I click this button, it initializes to a position of my choosing, a position which would result in a very short game, basically. But we can run some games where the initial positions are randomized during questioning. So when we click the Start button, it opens up a window which prompts the user to choose between 1-step and 2-step minimax. We're going to go with 2 here. So as you can see, white's first move has been done. Let's click on the tree of minimax, and then let's click on the down arrow key. What this does is it basically makes it so the window focuses on the root node of the tree of minimax. If we click the down arrow keys and the up arrow keys, we can basically traverse the levels on the tree. And if we click the right and left arrow keys, we can traverse all of the nodes inside of this particular subtree. And then let's go all the way to the right. Here we have a node which is connected by 2 green lines. This is actually supposed to be a green node, but the reason why it's bolded and in black is because the window is currently focused on this particular node. But anyway, so this node is green, and what that means is that since this node is on the first level, it means that this is the move that was chosen by the AI. And as you can see, it doesn't stop there. If we go here, as you can see, it goes all the way down. There's at least 1 node on each level that is connected to this first node on the first level. And basically, I guess you could say that this is like a connected pathway, which showcases how it is that the AI came to choose this move. So let's go back to the game. So we'll click the next button. and it initiates either black's turn or white's turn, depending on whose turn it is. In this case, it's black's turn. And then let's just go towards the end of the game. Once we reach the end of the game, a window pops up which showcases one of the 5 endgame scenarios, and in this case, it's a checkmate. But let's say we wanted to replay the game over again just to see what happened. Well, what we can do is we can click the reset button, and it resets the state of the board back to its initial position before the start button was clicked. All right, so let's go back to the presentation now. Okay. So the image on the left is a UML diagram which showcases the structure of the program. And the image on the right is a legend which showcases all the possible relationships between the structures showcased in the UML diagram. Here, the image on the left is a color-coded UML diagram which showcases the time complexity of the program. The calculation of the time complexity was done using big O notation, where O stands for order of complexity, and all the variables inside of the parentheses represent different varying input sizes. The time complexity legend on the right represents all the different time complexities for the methods that are shown in the UML diagram. Every single line of code was taken into consideration when doing the calculations. So the calculations were done in great detail and with incredible precision. The calculations and the variables can be explained during questioning. So the overall time complexity of the program is O of n cubed times S times RP. And this is because it yields the greatest upper bound value out of all the time complexities shown in this table. So during the course of testing the program, scientific curiosity led us to wonder if increasing the number of steps in the Minimax algorithm would yield better results. Initially, we tested 30 arbitrary initial positions in both 1-step and 2-step just so that we could have a minimal statistical sample. Since we noticed that there are substantial differences between 1-step and 2-step, this led us to want to facilitate exhaustive testing instead of just having a minimal statistical sample. The process for producing results includes 3 steps. 1, attaining all the legal positions, 2, testing all the legal positions, and 3, gathering all of the results. So, a unique enumeration can be assigned to every chess positions. Enumerations are calculated based on the square that each piece resides on, and this positional value can range anywhere between 0 to 63, or in chess terminology, it would be between A8 to H1. The positional values of the black king, white rook, and white king are multiplied by factors of 64 to the 0, first and second power, and then the sum of all of these products would give you the resulting enumeration. So given the aforementioned formula, there is a total of 262,144 possible enumerations. However, not all of these enumerations are legal, and this is because this formula doesn't take into account the rules of chess. So in order to ascertain the legality of all these enumerations, 2 constraints are necessary. 1, check and checkmate are legal starting positions, since white always moves first, and it would result in an instantaneous loss for black. And 2, no 2 pieces can share the same square. So after filtering out all the legal enumerations, the remaining number of legal enumerations totals to 175,168. So all the legal enumerations will be used as starting positions during testing, and all of the games will be simulated without any need for human input. Since we tested the initial positions in both 1-step and 2-step, the total number of chess games to be simulated totals to 350,336. The program used to test all the legal positions is analogous to the main program with some differences. So firstly, all user interface aspects of the programs have been omitted to improve on computational performance so that the tests can be ran more smoothly. Secondly, additional functions have been added to be able to write the test results into files. These files would be named after their corresponding enumerations and would also contain the test results of both the 1-step and 2-step simulations of the initial position. The results of simulated games includes the number of steps used, the starting position represented in Fen, the list of all chess moves made written in standard chess notation, the amount of moves it takes for the game to come to a conclusion, and the outcome of the game. Here we have an example of an initial chess position being converted to Fen. Here we have an example of a full chess move being converted to standard chess notation. And here we have an example of, well, just different kinds of special cases when you write in standard chess notation. So the computer used to facilitate exhaustive testing came equipped with an Intel Core i7 64-bit processor with 32 gigabytes of RAM memory. Testing was done on 2 separate sessions and 2 separate days, and on each day we tested 87,584 enumerations. Each session lasted 1,200 minutes, so the total time approximately needed to complete the exhaustive testing was around 40 hours. So because we tested every single initial position, the results should be mostly accurate. However, all the legal enumerations have been tested only once. The randomization of moves with tied values could affect the results to some degree. So to ensure complete accuracy, a comprehensive set of test results would require about 30 tests of all the different initial positions. And this would include both the 1-step and 2-step simulations. And unfortunately, this was not feasible due to time constraints and hardware availability limitations. And I also calculated it would take about 50 days to run the exhaustive testing, which is just not feasible. So the results of testing. The number of checkmates from 1-step to 2-step increased by 74.54%. The number of 50-move rule draws from 1-step to 2-step decreased by 228.44%. And the average number of moves per game from 1-step to 2-step decreased by 35.14%. So 2 observations can be made from the obtained results. 1, there are no stalemates, rook capture draws, or 3-fold repetition draws. And 2, there's an increase in the amount of checkmates and a decrease in the amount of 50-move rule draws and number of moves per game. There's good reason for this. 1, well, let's just say that n represents the amount of steps incorporated into the Minimax algorithm. When the white king is n squares away from the black king, it can assist the white rook in delivering a checkmate by protecting the white rook while the white rook corners the black king. Conversely, the black king attacks the white rook when it is n squares away from it, because the black king would be awarded an endgame value of 1,000 for the white rook's capture. So basically, the 7-step hypothesis states that if games were to be run on 7 steps of Minimax, both white and black would play optimally, and this is because their calculations and their predictions would fall within the entirety of the board's 8x8 range. Moreover, if games are played in 7-step Minimax, the amount of checkmates would increase to 100%, and thus the average amount of moves per game would also decrease. And it's also worth mentioning that this hypothesis has already been published in the CIIT 2023 conference. So this table showcases the upper bound of the time complexities for all input sizes. O of n has the greatest upper bound and is exponentially proportional to the number of steps. Because O of n has the greatest upper bound, which can also be represented by 176 to the power of s, because it has the greatest time complexities of all the different input size variables shown here in this table, we could say that the Minimax tree is actually exponential in nature. So even though the exponential nature of the program has already been proven, one could actually argue that the time complexity for chess is constant. And this is because all aspects of the chess program are calculable and held by some upper bound. So for example, the Minimax algorithm is constant because you can calculate the maximum number of nodes needed to be sorted for choosing a move. Like, for example, in 1-step Minimax, the upper bound would be 176 nodes. And in 2-step Minimax, the upper bound would be 30,976 nodes. So this calculability is actually applicable to all the data structures that are used inside of the chess program. And thus, all the data structures are hard-bounded to some maximal value. Additionally, in 1950, Claude Shannon calculated that chess has about 10 to the 120th power unique possible games. And this is also known as the Shannon number. Because chess is actually a name which has, or because chess is actually a game which has a limited number of combinations of possible moves, one could surmise that chess is actually O of 1, or constant time complexity. So for future work, alpha-beta pruning may need to be incorporated since it would cut out several subtrees from the tree of Minimax, which would improve the computational performance by lessening the processing workload. Also, the amount of calculations that need to be done increases exponentially with each additional step. So a supercomputer may be necessary in order to facilitate exhaustive testing on the 7-step hypothesis in a reasonable amount of time. It's also worth mentioning that all the data structures and operations which are done in this program are done with a linked list. So maybe using an alternative, more optimal data structure could improve the performance of the program. So thank you for your attention. Do you have any questions?
Thank you, Filemon. Do you hear me? I
Yeah.
am not. Okay. Thank you, Filemon, for the very precise and I would say well thought and very good presentation you did. So now it's time for posing the questions.
Okay.
I would first give the floor to the colleague, Professor Ivan Petrov. So, Professor Petrov, please, the floor is yours.
Thank you, Professor Irena. Great presentation, Filemon. I have several questions. One of them is, are there any other algorithms that actually can be used instead of Minimax? Did you consider them? And the other question is also related somehow to the first one. Why Minimax is the most suitable, if there are any other? So you could actually try to answer of these two questions. And then the last question that I will have is that what about the start of the complete new game? Because you're actually looking of only 2 figures here that actually are chosen and their moves are actually evaluated according to the spanning tree algorithm and so on. But what about considering a whole new game and how the move is actually chosen? Is it actually randomly, or there is some kind of default strategy that the player would have? And what is the initial state of the simulation when it's actually most appropriate to be used? What you have actually has actually considered to your dissertation, when actually is the initial state of when this algorithm can be used and optimized?
Okay, well, let's just answer the questions one by one. All right, so I think you posted them here in the chat, correct?
So far, yeah, it's posted. Okay, thank you, Filemon.
Okay, so let's see. Are there any other algorithms that can be used instead of the Minimax, and why is the Minimax the most suitable? Okay, so truth be told, the decision to use the Minimax algorithm was kind of completely arbitrary. There's actually kind of a history behind this chess program. It started out with the father of Professor Adrijan Bozinovski. He had some kind of chess program which was written in Fortran like a long time ago. And this was a project that I took up a long time ago. It started out as an algorithmic program. So every single situation in this endgame situation was accounted for. It was completely hard-coded, basically. And then after that, we decided to move to a heuristic version of the program where we had a position evaluator, but it worked differently. It was separate for white and for black. It was completely separate. And we also used something that resembled kind of an A-star search algorithm. So yeah, this is basically, you could say, like an improvement. We're basically trying to, we went from an algorithmic version to a heuristic version, and then to a version that incorporates some kind of AI. But we just arbitrarily chose the Minimax algorithm to try to incorporate the Minimax algorithm. So the next question is,
there are other algorithms that actually could be used.
Well, yeah, there are. But in this case, we decided to use the Minimax algorithm and to see what would happen. But I'm not sure. We could experiment with other algorithms and test other algorithms, but that would take time. Not just in implementing the algorithm, but also getting all the test results as well. The time complexity might also be different. That's also something to take into consideration.
Behind all of them is spanning tree actually decision making.
Sorry, could you say that again?
Spanning tree decision making is actually behind of them at the end with the nodes, and there actually are first level, second level of decision,
Yeah.
depending of the move of the player and so on.
Yeah. Wait, so this next question is, what about the start of the new game? How the move is chosen? Is it random or is there a default strategy? It's entirely dependent on the tree. It's dependent on two things. So basically what white wants is white wants the move with the smallest number of free squares and the smallest number for endgame values. So basically the smallest number for endgame values would be -1000. Like, let me go up. My screen is still being shared, correct?
Yes.
Let me see. Where was it? Yeah, so checkmate is -1000. So basically it's aiming for the lowest possible number of free squares, and it's aiming for this checkmate if it can sense it, basically. Because like, for example, how do I explain this? Basically,
Okay,
the number of steps incorporated is basically how many moves can it look ahead. So if it finds a move which not in the first level, but on the second level after, or not the second level, the third level. For example, there's 2 steps of Minimax. So we can see one move ahead, and we choose that move. And we choose that move because, for example, we can see a checkmate after that. Like, let me actually go to the program. Let me go to the program really quickly. So, for example, we have this move here. This is the move that has been chosen. Why? So this is white's move. We go down to this level. Now it's black's move. And now we go down again. And this is white's move. And as you can see, it's -900. And this basically signifies a checkmate, but it happens later in the game. And so basically the reason why white chose this move, as we can see here, is because it can see that checkmate. It knows that there is a checkmate available for it if it makes this move. So that's why this move was chosen, for example. And then black is the opposite. It basically just chooses whichever moves maximize the number of free squares that is available to it. And it also tries to choose any move that has any of the 4 drawing scenarios. So stalemate, 50-move draw, rook capture draw, and 3-fold repetition draw. So this is the basis for how white plays and how black plays, essentially.
so okay, they're actually preset.
Yeah.
First use minimalistic approach, then the other one maximal approach of the free squares that actually it will have.
Yeah, pretty much.
Okay.
So let's see. What else do we have? What about the start of new game? How is the move chosen? Is it random? Are we talking about the initial starting position? Are you referring to the initial starting position here when you ask about the start of new game?
Well, yes. I thought on the initial starting position, depending on the moves of the all figures, and then when actually is the initial state of the simulation, when actually the algorithm that you're actually using is going to become suitable for the game.
I'm not sure I understand your question. Like, if you're asking about how
Okay, I'll get short. What is the initial position of the figures that you're observing when actually the algorithm is usable?
the algorithm is
The initial scenario that you actually have it here, that you're actually analyzing, that's
Right.
actually the position when the algorithm is usable. Yes.
yeah.
Is this the set of the if this is the set of the figures that you actually have? One king, rook, and a
Yeah.
king.
Yeah.
This is it. So when
Yeah, this is it.
when actually you will have all of these figures at the board, then your algorithm will start to be employed.
Actually, oh no. So basically, when I click new game, it just chooses some random legal starting position. It actually starts when I click this 2. Like, for example, when we choose
Okay.
2 steps of Minimax, then the algorithm starts.
Okay.
And then the method for the Minimax is invoked. So yeah.
Okay, thank you.
And then, oh, I guess I answered all the questions. Okay, thank you. Thank you very much for your questions. I appreciate it.
Thank you.
Okay, thank you, colleagues. Now, since your supervisor has already posted his question, and I'm trying not to post them all in order not to make you lose concentration, I will ask Professor Bozinovski to ask his question and discuss about your work, and then I will be the last one. Thank you.
Okay,
Professor
thank you,
Bozinovski.
Irena. Sorry for the posting of the question to everybody. It should have been to Sonia personally, so as not to derail you. But yeah, the question is that to explain in more detail how the time complexity was calculated, because there were a lot of letters being used, which is not something that is done every day. And this is something to showcase that we actually did a lot of work there. It is not just arbitrary, it is not random. That was a lot of time spent. And just to please explain how it went. The second question is about something you said at the end, that you used the linked list data structure. So why was that used and not something else? I mean,
Okay.
to use a linked list in order to build a tree is not standard. I mean, usually nodes are used and
Yes.
links are used. So
Yes.
linked list to build a tree is unusual. Please explain why you did that. And my third question would be something for the future, in a sense that how would you expand this program to other chess endgames? I mean, this is king and rook versus king. And the other three basic chess endgames are king and queen versus queen, and king and two bishops versus king, and the king and bishop and knight versus king. So how would this kind of approach be applicable to other chess endgames as well? So those are my questions.
Okay, let's see. So, the time complexity. Okay, well, I guess the first thing that I'm going to need to explain is probably the variables. So O1 is pretty self-explanatory. It's constant time complexity. O of S basically represents the amount of steps. And for example, in this table, we're saying that, okay, this is the upper bound calculations for the time complexities of all input size variables in one step. So in this case, O of S would just be equal to 1, but it can be equal to something else depending on how many steps we use. 1, 2, 3, 4, whatever amount of number. L actually refers to the amount of levels in a tree of Minimax. So basically, the upper bound calculation can be represented by the formula 1 plus 2s, where s is equal to the amount of steps. This was actually something that I already mentioned when explaining clicking the tree button. So yeah, O of L stands for levels. So for example, if we have one step of Minimax, the depth of the tree would be 3. O of L would be 3. And then 1 plus 2 times 2 steps, that would be 5, and so on. So basically, O of L represents the depth of the Minimax tree. Next, we have O of B. So basically, O of B stands for board, and this represents the total amount of spaces between the piece and the edge of the board. So the maximum possible value for this is 7. And then next is O of KP. So KP basically stands for king piece. We do have more than one king, but they both can have the same number of moves. So basically KP stands for the amount of moves that the king pieces can make maximally. So in this case, it would be 8. Next, we have O of RP, rook piece. The maximum amount of moves that it can make is 14. And then O of F is free squares. So it stands for free squares, and the maximum number of free squares that we can have is 52 free squares. Finally, yeah, so this is O of N, and O of N stands for nodes, and this is represented by the formula Wm times Bm to the power of S. So it's basically the maximum number of white moves that can be made on one level multiplied by the maximum number of black moves that can be made on one level. So that would be 22 white moves multiplied by 8 black moves. So we would have a total of 176. and that would be to the power of s. And s is something that can be, well, it can be decided. So basically O of n is equal to 176 to the power of whatever number of steps that we use. So that's basically how all of the variables for all the time complexities work. Moving on to your next question, why did you choose a linked list as the data structure of choice? I'm going to be totally honest here. It's because it's the data structure that I felt most comfortable working with. It felt the most intuitive for me. I have the most experience with it. But, you know, looking back, I wish that I would have known, I wish that I would have realized how actually important it is, because we're working with such a large input size here, and it's actually important. Like, I felt like most of my time during my studies, my focus was, let's just make the program work, right? But now we're dealing with ginormous input sizes, and being optimal is actually relevant here. Like, we need to be optimal because, for example, with like exhaustive testing, or if we just want to run on 7-step Minimax, that would be 100 and what is it? 176 to the power of 7. That is a gigantic number. So in order for us to work with that amount of nodes, I think, yeah, it would probably be preferable if we did take a look at all the different possible data structures and see which one would be the most optimal to use. But given the amount of time that I had, I just decided to use the linked list data structure because it felt the most intuitive for me. So that's the answer to that question. So the third question is, how would the program be expanded to other chess endgames? Well, let's see. I guess honestly, the most important thing here, I don't think it's not really a matter of programming it. Programming is pretty self-explanatory. Like setting up criteria, for example, would be self-explanatory. What would be important is to really understand how chess works here. Like, more than anything, the most critical part is understanding chess theory and how the pieces work, and like what's the most optimal way to use certain pieces. Like, for example, instead of a rook, we have a bishop. Like, what's the most optimal way to use that bishop to get a checkmate? So basically, yeah, it's not really a matter of like how would the program be expanded, but I guess it's more like how would my knowledge of chess theory be expanded, and like basically just trying to understand how all of these different endgames work, and then developing the appropriate criteria so that we could basically accomplish a checkmate as soon as possible. So yeah, that's my answer to that question.
Okay, thank you very much.
Thank you. Thank you so much for your questions.
Okay, thank you both, and thank you for answering, Filemon. So I guess it's my turn now. First of all, Filemon, I would really like to show my satisfaction and respect for the work you have done.
Thank you so much.
It's difficult to make such a work. In particular, using these heuristic functions, and we'll know how problematic it is to pose it and to detect all that stuff, and how time consuming is. So congratulations from my side.
Thank you so
I'm aware of
much.
that one.
Thank you.
In that sense, I will not go into the details like the previous two colleagues, because I have it clear what you have actually done here and how much time you have spent it.
Thank
And
you.
from the previous answer, I also have it clear that you completely control above the work you have done, and I have no doubts of that.
Thank
So
you
my
so
first
much.
question would go into the direction of further research, but because I really believe that, in particular, what you have mentioned now, so I'm linking to your last sentence, how should you use the knowledge you have learned during your work on this thesis for your future work, for future development, for future scientific work, or any other work you wish to you would plan to do in the future. My first question is related to these algorithms. Have you ever thought if it is possible to increase the performance of your model by involving genetic algorithms?
Genetic algorithms.
In terms of
Genetic algorithms. Here's the thing. I'm gonna be honest. I actually don't know what that is, and I would like it if you could elaborate and tell me more about genetic algorithms.
Okay. It's about, you have the heuristic function, and then they here the problem is that we don't know the function, no, and then they intercross. So the players the decision making and the position depends of n parameter, for example. So there are some places when they cross between each other, no. And now, for example, the background is, because I will not take time now to explain it, but the idea is to involve a function, you can Google it, such that if a performer, if a player is good, then he remains and he eliminates the others, the ones that they are not doing well, the position that they are not. You can think about it.
Oh, it sounds kind of like pruning the subtrees, like some subtrees.
Exactly, but you can Google
okay.
it, and it will be a good idea just to think about it. Okay, maybe you can link with your supervisor. Just an idea. I think that I somehow think that it might improve your work. And
Definitely.
I would even motivate you. I would even motivate you further on to think about. So my second question is, if I know that it's difficult to answer it now, but also posing it, if you can answer immediately or think about it. I think that the best giving back to society, starting to giving, we all do research to give back to society. I mean, no other motivation down there. We're not rich, definitely.
Yeah.
So, can you think of maybe about some real life problems that might be solved by the use of such models, in particular the model you have developed, and involving then the genetic function and so on, because that would be the best shot. Actually, you said that you would like to use this knowledge of Shah and everything you have learned to master in that field, but I would really like to invite you to have a kind of a broader picture, that maybe that can be somehow analogically transformed, transmitted into solving or posting some real world problems and solving it. Maybe to name a few, I invite the other colleagues maybe to involve in this discussion. Maybe they have some idea now to tell you and to help you, because I think that would be maybe the best shot, not to have just do you understand me, Filemon?
Yeah, I get it. So like I understand what you're asking, but basically, when I think of this Minimax algorithm and like just like this AI in particular, I always think that like it would be incorporated into like any 2-player games, basically.
Exactly.
Yeah. It would, like I know, I think Go, Shogi, there's like other games besides chess that this algorithm can be incorporated into. But I think probably the most eye-opening thing is realizing that like optimization is probably the most important thing that I got from all of this. Not necessarily, I mean, it was nice learning about a topic that I really didn't know much about, and it would be nice to like broaden myself and to get into like even more complicated algorithms and topics. But I think the most eye-opening thing really for me was like how important time complexity is. Like time complexity is incredibly important. Like there was at one point during exhaustive testing, well, not during the exhaustive testing, but before it, I realized like how slow it was to run things on 2-step Minimax, like way too slow. It initially it was not going to take 40 hours. It was going to take like more than a week, maybe like 10 days even maximally. I'm like, oh my God, what am I going to do? So I realized, okay, all right, I literally told my father about this. I'm like, oh, the time complexity must be awful on this. And I realized, okay, you know what? I'm going to go through every line of code and I'm going to see, well, rather what I'm going to do is I'm going to add debugging comments and see, okay, where does it get stuck?
Yeah.
Where does it get stuck?
Yeah.
And then I'm going to be like, okay, now how can I fix this? How can I make this better? And literally with just like 1 or 2 changes to the line of code, the time complexity completely like changed. It was so much better. It ran so much more smoothly. And I was so happy. It went from being like 7 to 10 days to just like under 2 days, like 40 hours basically. And I was thinking that I was going to have to use so many computers in parallel to do all of the exhaustive testing, but it turned out I only needed to use one. Just because I was able to change the time complexity. So
exactly.
Yeah.
Exactly.
So
and you have just described what you felt during the process is what we all feel when we do research. I mean, the excitement is like above everything, and I'm very happy that you were, I would say, really honored to feel that during your master process. Normally, it's something that goes within the PhD process making, because the master should be a kind of a lighter research or research. But I'm very happy that you were privileged to, and I would really advise you to continue with since you have that passion within you, to continue with research, no matter in academia or maybe some corporative research where you will be richer, definitely. So think about it well, or maybe both. Okay, Filemon, thank you. I'm satisfied. My last question, which is maybe a kind of out of topic, but not so out of topic, and I'm asking it more for making my own statistics and curiosity within the time we live in. So it's personally your opinion, nothing to do with the. You have answered my questions, and I'm very satisfied. What do you think about? How do you think shall we involve AI in a near future, in a next academic year, in next 5 academic year, not just in academia, but in all the educational processes? To improve it, because it's obviously that the 20th century industrial revolution education system will not work globally. I'm not talking about our country and the educational system. I'm talking globally. So have you ever thought about that? And I would really like to know your first opinion. Don't think about it. You're a student, and I would like to know what do you think about that.
Okay. I definitely think I've had this discussion before about AI. Now, about the subject of AI. Okay. When I think about AI, I mean, for example, let's take a look at the most recent example. I don't know if you've heard of it. You probably have ChatGPT.
Of course. Not me. All our students here, all our students are using it. The idea is how to involve it to help them learn, and not to help them not to learn. Okay.
Yeah. Oh, how to? Okay.
Okay, that's like my question. How should, if you were a professor, imagine you're a young assistant, how would you evolve exactly ChatGPT in your lectures, in your curricula, to involve it within the educational process, in order to inspire critical thinking, creativity, and so on, and not to be abused by students. And you have to make it in a month.
Oh my God, that's rough. That's really rough. Yeah, like honestly, it sounds really difficult. This is one of my main problems with AI. You know, I like AI and I find it so interesting. And I like, for example, with chess, we've managed to find, like, with AlphaZero, new openings that we've never even seen, like that we could have never came up with in our entire lifetimes. And that's one of the beautiful things about AI. We can use it to, like, learn. We can use it to learn more. But then there's people that use it unethically, and there's people that use it to cheat. And that's kind of one of my problems with AI. And I actually, to be honest with you, I've got no idea how I would be able to to motivate people to use AI to be more creative, but not to do all the work for you. And it's so commonplace. It's so commonplace. I see it all the time.
Okay, for your information, it is starting January. It's the most up-to-date topic in all the university worldwide, but not
Really?
only not only regarding ChatGPT, just the beginning. It's how to reorganize academic education in order to involve all the upcoming and to remain creative and critically oriented, because this is the only place where we can work actually, no?
Yeah, like I feel like what I really liked about AI is
Mm-hmm.
just seeing what it's capable of. Like if I had a curriculum, I guess uh the most important part would probably be like the first couple of classes, or rather just the first class, just showcasing like what AI is capable of. Like all of the
Mm-hmm.
greatest achievements of AI, showing what it's capable of. Maybe that could inspire like some students. I mean, of course, the curriculum is going to involve explaining all sorts of different aspects about AI. But
Mm-hmm.
I think the most important thing is like the first impression. You want to give a good first impression about AI. And to do that, I think, yeah, showing all the different kinds of amazing achievements would be a perfect way to like introduce students to how awesome AI can be, basically.
Thank you so much, Philemon. I agree with you. Thank you for your extensive answers, not just mine, but to all the other colleagues. Does somebody now, regarding the protocols, I will ask the audience, does somebody else have some questions? No? Okay, so Philemon, you don't need to log off, because we're gonna just take a minute to post our results regarding the part of our grades, the part of your today's presentation grade. So I will ask the committee, if they haven't done it, to mail. Just give us a few seconds, and we're done with the grade. To mail to Sonia their grade regarding your public defense today, and she will take a minute or so to calculate your total degree, and then we go to the best part. Are you prepared, Philemon? It's once for a lifetime. The next step is PhD. I'm sure that you're gonna make it. I have no doubts of that. The question is when, where, and so on, and in which field. I mean, in AI or something connected, but maybe in something that will bring you academia and corporate finance at the same time. Think about it well.
Yeah, of course I
Okay.
will.
So Sonia, are we prepared?
Yes, we have the final grade.
Okay, and you have already posted to me. Okay, I'm seeing it. Okay, so now if we would have been in a classroom, I would have asked all the audience to stand up. So please imagine that you are, because it's a very important moment, which I'm going to read now. So, Philemon, by virtue of authority of the university and nominated by the faculty, Filemon Jankuloski, having completed his studies and satisfied the requirements prescribed by the faculty, has been awarded the degree Master of Science with all the honors, rights, and privileges thereunto appertaining. I hereby confirm that the candidate had successfully completed his course requirements and defended his master's thesis in front of a three-member committee consisting of Professor Adrijan Bozinovski, PhD, Professor Ivan Petrov, PhD, and Professor Irina Stajmenovska, PhD. I also inform you, Philemon, that you got the biggest degree, which is passed with distinction, which is not very common degree. The School of Computer Science is giving. You are one of you, I would say, during all these years, and I sincerely congratulate you for that one. I will repeat that it is completely deserved.
Thank you so much.
You have done a lot of work. You have had a great presentation. I wish you a lot of success in your further research, in your private life, and stay as passionate as you are as long as you can regarding the research. Thank you, Philemon. It was great
course.
having you as a student here. Thank you.
Of course. Thank you so much. I really greatly appreciate
Congratulations,
this.
Philemon.
Thank you so much.
Your final grade is a 95.38.
Oh,
Which is
wow.
definitely the biggest grade. I mean,
Biggest,
the
the
colleague
biggest.
Bozinovski can maybe comment here. Sonia is also has a great experience with the thesis, but I think that it's the biggest grade ever. No,
Yes.
That's
in
insane.
our, at least in School of Computer Science and School of Computer Science.
And
So
I
you should
hope,
really be
Wow.
proud of yourself.
yes, and I hope
That's
you will be on graduation to have your summa cum laude certificate.
oh 100%. Yeah. 100% I'm gonna attend. I'm so excited for all of that.
PhDF
This is
recommendation and
oh my god.
commitment.
This is insane. I honestly have no words. Honestly, I walked into this with zero expectations. I just said to myself, just do your best. You know, my parents even said, read the documentation, go over your code, do all that. I'm like, no, I'm just gonna memorize my presentation, get ready for that, and then I'm going to do what I can. You know, do my best, do what I'm capable of. I really wasn't expecting to get distinction. I'm beyond thrilled to hear that. This is like one of the best days of my life, easily. Thank you so much.
Bravo.
Philemon, congratulations from my side too. Wishing you all the best. Hope that you will proceed with your education. PhD is next level that you could achieve. You're capable for it. All you have to do is make the hard work count.
Of course.
Best of luck. Yeah.
Of course. Thank you so much, everybody, for taking the time to come here and congregate so that we can have this defense. I appreciate it so much. I know it was a very last minute thing, but yeah, you don't know how thankful I am that I was able to have this defense today. This is just this is incredible. I appreciate it so much. You guys have no idea. Thank you so much.
Filemon,
Thank you.
Filemon,
So
remember the first version? The
oh
algorithm?
yeah. Yeah, that was
Remember
hard.
the months, remember the years, remember the second version, remember the 4 papers that we made on this, remember
Yeah.
the formulas that we chunked, remember the conversion to heuristic,
Yeah.
remember the hardships,
Those
remember the days, remember the 17 hours of the coding streak.
oh yeah.
Brought this baby home, Filemon. We did it.
I'm so happy you were able to be here for this. Like this is a very important moment for me, and I'm just like really thankful that you were able to be here for this defense and stick around until the very end. That's like this was a very key moment for me, and we both worked really hard on this up until the very end. So I'm like beyond grateful. I also I want to give acknowledgments to Adrian. Like he has been a great professor, not just for the thesis. He is definitely a big role model for me, and he's taught me so much throughout all these years. He's been there for me in many ways, not just as a professor. He's also been there for me as a friend as well. He is just incredible, downright incredible. And my parents too, they gave me so much support throughout this whole thing. I've been stressed out like during so many points in my studies, but this was actually the least stressed out I've been. And this was the one time where my parents were more stressed out than I was. And yeah, I want to thank them for being there for me this entire time. We've been through so much hardship, especially through the pandemic. The pandemic was really hard on everyone. There was a lot of loss, a lot of grief, but thankfully my family and I were able to make it through it, and I was able to push forward and stay motivated and keep true to my work ethic, basically. So I'm really happy. This is really just a culmination of like the 5 or 6 years that I've spent at UACS, and I'm really grateful. Actually, learned so much while staying at UACS, and I'm really honestly excited for the graduation. This is also going to be one of the best days of my life, surely. Thank you so much, everybody.
Thank you, Filemon. And you have growth as a person as well, which is also very important. That's something that through the whole process. Thank you.
Thank you so
Okay,
much.
thank you, Filemon. We wish you a great day. So celebrate all day long. You completely deserve it. Have a
Thank you
great
so much.
evening as well.
Of course.
Thank you for all who were. Thank you to the colleagues, of course. Thank you, Sonia, for organizing